No, we should enter. We should enter slash. Yeah.
Are we starting?
I think we're starting soon. Yes, I think everything looks okay. So we should start, right?
I just need to announce there too. Hello, everyone. Welcome to this seminar class. Just a quick announcement. Today, you're only going to have 2 presentations instead of 3. So I guess you're going to stay here not until 7 p.m., which is great. I guess we are going to start with the next one, or the first one, which Haosong is going to announce.
Hello, everyone. Let's welcome Joseph. He is a third-year bachelor student in computer science. He's interested in computer systems and optimizing software performance. He's going to present a paper on silent data corruptions.
Does this work? Okay. Okay. Hi. So today we're going to be talking about this paper, Understanding Silent Data Corruption in a Large Production CPU Population. This was written by a number of engineers from engineers at Alibaba, and was presented at the Synopsium on operating system principles in 2023. Okay, so just a brief outline for what we're going to be discussing today. First, we're just going to look over some background on what silent data corruption actually is and what the motivation behind this paper was. Then we're going to look at see a brief executive summary of the structure of the paper. Then we're going to go into look in more detail at the observations that were made in the paper and some of their proposed enhancements they came up with based on their observations to improve their testing strategy. Finally, we're going to look at some of the strengths and weaknesses of the paper, and at the end, we'll have a brief discussion. That's it. So first, some background about silent data corruption. So what actually is silent data corruption? Well, basically, silent data corruption is any kind of data corruption that is silent and that we don't have any kind of signal that it occurred. Typically, this would mean, for instance, we have an add instruction. We add 1 + 1 and it gives 3. However, the important part and distinguishing factor is that there is no exception or fault raised. The software is not aware that anything went wrong, and computations will continue running as normal. It's important to distinguish that these are not caused by any of the quote unquote usual things that we're used to having as sources of corruption. It's not happening in memory or on the network and disk. It's caused in the CPU itself by manufacturing defects. And these are becoming increasingly common and problematic when operating at large scales with large numbers of CPUs. They're bad because it breaks the fundamental assumption that lots of software makes, that the CPU is fail-stop, i.e. if something goes wrong, the CPU will crash. Most software assumes that as long as the CPU is continuing to work, that it's working correctly. And even though they may assume that other stuff might fail, they generally assume that the CPU is correct. And it's problematic because, yeah, if we have undetectable data errors, the computation could continue for a very long time before the error actually becomes noticeable. Maybe the incorrect value might be stored into a database somewhere, and it might be months later until someone realizes that one data point is very far off. So here's some examples of silent data corruptions that were described by the authors of the paper. Importantly, they mentioned 2 different instances of checksum being computed incorrectly. In one case, it was due to a faulty instruction. One of the instructions that was used while computing the checksum occasionally gave the wrong value. And the end result was that the machine in question kept resending the same request over and over again, because every time it downloaded the data, the checksum was wrong. Another machine was computing a checksum incorrectly, not because of a bad instruction, but because of bad cache coherence. They had one thread that was writing it into a buffer and another thread that was reading data out of it to compute the checksum. However, due to the fact that the cache coherence was not functioning correctly, the reader thread occasionally saw inconsistent data in the cache and read the wrong value out of it. And the checksum at the end ended up not matching. Another case that was described was an instance of incorrect encryption and decryption, specifically in AES instructions. There was one specific core which, when encrypting data, could decrypt the data again, but attempting to decrypt that data anywhere else resulted in garbage. So this isn't a new concept. There have been some existing small-scale studies and theoretical studies of silent data corruptions. However, there's only really been two other existing works that have actually looked at this phenomena at a large scale. Specifically, one paper from 2021 from Google and another paper from Facebook, also in 2021. It's important to note that neither of these papers actually publish many concrete numbers or specific values. They're all very vague with their actual details of what they've measured, presumably for some kind of business considerations. Okay. So here's a summary of the actual paper itself. The authors noted that basically overall, silent data corruptions can cause significant problems in production systems, and there's a limited understanding of how and why they occur in the wild, and when what their effects could be on the system as a whole. Their objectives were to analyze silent data corruptions and their effects on software at a very large scale, and at the end to propose a concrete approach to help mitigate or at least reduce the overhead of attempting to test for silent data corruptions. Their main idea was simply they have access to a large fleet of over 1 million CPUs from a variety of different vendors, implementing different instruction sets from a variety of different ages in different data centers, and they wanted to evaluate some of the observed SDC instances that they'd seen. And at the end of the day, they managed to come up with an improved testing strategy using their observations that they made, which was more effective than their existing approach, yet managed to do that with substantially less overhead. Okay, so what did they actually manage to see about SDCs? First of all, they simply looked at how often do these occur. They found that 3.61 basis points, that's 3.61 per 10,000 CPUs, actually cause or experience SDCs. This number is roughly consistent with both of the Google and Facebook papers, as long as you are somewhat generous with their very vague interpretations. It's within the same order of magnitude, so that's probably as close as the correlation as we're going to get. But we can conclude from this that all of them, everyone's experiencing them at roughly the same frequency, so the silent data corruptions are a pervasive and industry-wide issue. Quick side note on how silent data corruptions are actually detected. Typically, clients, in this case data centers, do multiple rounds of testing after purchasing a CPU, in addition to the testing which is performed by the manufacturer. And then also, once the CPU is actually in production, they'll typically run testing at regular intervals every couple of months to ensure that the CPU is still functioning properly. The authors found that most of the detected faulty CPUs were actually able to be detected during their pre-production tests before the CPU made it into production. However, there is still a worrying number of CPUs that do make it past all of those testing and aren't detected until the regular tests. And of course, none of this is accounting for any CPUs that aren't caught during any rounds of testing and simply have undetectable faults. Next, they broke down the failure rate by microarchitecture. They found that silent data corruptions affect CPUs of all microarchitectures from all vendors, and they note specifically that the rate of failure hasn't been decreasing over time. So that would seem to imply that if manufacturers are aware of these issues and attempting to mitigate them, that their mitigations are either ineffective or simply not effective enough. Next, they look at how many cores are actually affected by SDCs. They distinguish basically the SDC may either affect a single core, which is typically caused by simply a defect in a non-shared component, only isolated to that core, for instance, an ALU. And there's other faults which can affect multiple cores. Typically, this would be a fault in some kind of shared component, like a cache. However, they did mention that there was at least one instance where they found a CPU which had the same fault in the same components on every core. They claim that the rate of multi-core versus single-core failures is about half. So about half of the detected faults affect more than one core. This is interesting because it conflicts with the Google paper. The Google claims that typically only one core fails. The authors attempt to explain this difference by hypothesizing that Google's test framework isn't as good at detecting cache coherence problems as theirs, but we don't know for sure, as we don't have access to either test framework. Next, they break down the CPU features that are most vulnerable to silent data corruptions. They find that the most vulnerable ones in order are vector operations, floating point operations, arithmetic logic unit operations on the ALU, and then finally cache coherency and transactional memory operations. It is interesting to note that vector operations are the most affected, even though the ALU is still quite vulnerable. This will, I'll go back to the vectors and the FPUs in a moment. Because they then broke down the affected data types. They found that SDCs do affect all data types, but they don't affect them all equally. In particular, floating point operations are affected disproportionately. And they come up, their main hypothesis for why this occurs is simply that floating point hardware tends to be more complex than integer hardware. For instance, floating point division or trigonometric functions. These are all a lot more complicated than most integer operations. This does seem to add up because they do find that SDCs typically occur in the mantissa part of the number, which would typically have more complex hardware behind it than, for instance, the sign bit or the exponents. On the other hand, because the SDCs typically only occur in the mantissa, it often results in only a minor loss of precision. Whereas as the mantissa does not have as most of the mantissa does not have a particularly significant effect on the total value of the integer, of the floating point number. We then go more into detail on that by breaking down the actual individual positions within the number representation, which are most vulnerable to SDCs. By looking at specific CPUs and test cases which have recurring bit flips at the same position due to SDCs, we find that in fact, yes, there are a substantial number of bit flips concentrated near the center of mantissa on floating point numbers, or off to the least significant bits, while the exponent part, which would be on the left, is basically unaffected. The authors don't attempt to explain this odd spike at the around bits 8 and 9 of integer operations, but they do just in general hypothesize that the hardware defect which was causing the SDC causes some kind of deterministic influence. Whatever that might be is left up to future works. They then note that the number of bits flipped by a single occurrence of a silent data corruption is often greater than 1. In particular, there's actually a substantial number of bit flips, SDCs, which result in more than 2 bits being flipped, which is worrying because for reasons that we'll also get back to in a moment. But next, they look at the occurrence rate and frequency of silent data corruptions. They find that the occurrence rate varies significantly depending on the actual CPU or fault in question. Some SDCs can be reproduced less than once per hour, while other ones occur more than hundreds of times per minute. They find that around 50% of the time, the SDC can be reproduced more than once per minute. From this, they do derive that SDCs can repeatedly and often occur in production, which, as they've seen from some of their case studies of examples of SDCs, this can have a large impact on the operation of the system as a whole. To try and explain the less frequent SDCs, they note that there is a correlation between the temperature of CPU's operating temperature and the occurrence rate of the silent data corruption. Specifically, they find that the logarithm of the occurrence frequency is more or less linearly correlated with the CPU's temperature. This helps explain a number of issues that they'd found, which had seemed inexplicable at first, yet later turned out to be temperature related. For instance, in one case, they found that other cores being busy increased the rate of a particular core causing silent data corruptions. And the more cores that were busy, the more that one core had errors. This was eventually turned out to be simply the other cores being busy caused the CPU's overall temperature to increase. Another example included the order in which testing would run could affect the SDC rate because some test cases cause the CPU to get warmer than other ones. So if a test case which generated less heat was run before a test which found an error, then it would be less likely that the second test would find something if the CPU weren't preheated by the test case, which causes it to get warm. Also, for instance, they found that optimizations to their testing framework itself could cause the CPU to generate less heat and in fact cause the test cases to cause fewer errors, to detect fewer errors, even though the test cases themselves were unchanged. Based on this observation, they basically distinguished two different kinds of silent data corruptions. They find that there are so-called apparent SDCs, which occur from starting at a very low threshold temperature and occur very frequently, and tricky SDCs, which require a high temperature before they start to occur, and even then they are typically fairly infrequent. It's important to note that it is easy to test for the apparent SDCs because they don't require any special conditions and they happen all the time. However, the tricky ones are difficult to test for because they require long rounds of testing at high temperatures. This is bad because it means your tests have to run for a long time, which prevents your CPUs from being used for useful work, but also operating at a high temperature for an extended time could cause more damage, could cause the CPU to be damaged as well. Next, they note that most of their test cases in their test suite actually never detect anything. In particular, 560 out of their 633 test cases in their test suite have never detected any SDCs on any system they've tried. This number is even more extreme if you break it down by the individual CPU microarchitecture. The authors guess that this is because all CPUs in a batch or of a particular microarchitecture are more likely to be vulnerable to the same kind of faults and could therefore be affected in a similar way, therefore would be detected by the same test cases. On the other hand, they also note that there are some CPUs that they know have faults, yet are unable to pick these up using any of their current tests. The authors hope that at some point in the future, this would no longer be a problem as their test suite continues to mature. However, for now, it does show that we cannot detect all potential faults using testing unless we have some kind of theoretical exhaustive test. And finally, they note that existing data corruption mitigations are ineffective in the presence of silent data corruptions. For instance, erasure coding, which is a technique often used for things like RAID arrays, can only be used for data recovery, but it can't detect errors, nor can it repair them. Techniques like ECC and checksumming assume that the data is correct when the checksum or parity bits are being computed. If that's not the case, then your checksum is basically worthless, as it's helping you correct incorrect data. Additionally, standard ECC is insufficient because, as previously noted, multiple bits can and often do, in fact, get flipped simultaneously, whereas standard ECC is typically only capable of repairing single bit errors. And to top all of that off, when computing checksums and other things, many implementations make extensive use of vector operations, which, as they had previously found, are the most vulnerable to silent data corruptions. All right. So now that they've made these observations, the authors proceeded to try and use these observations to enhance their existing testing workflow. They compared it with their baseline, which is simply how tests are currently done in their data center. It's quite simple. They run all of the tests during pre-production and again every 3 months. The test cases are all prioritized equally, meaning they all run for the same duration. And if any detective core is identified, they remove the entire CPU from their network. So their enhanced testing system, which they have named Farron, basically makes three main changes to this. For starters, in addition to regular testing, they attempt to limit the occurrence of tricky STCs that may have gone undetected by reducing the core's operating temperature, with the objective idea being that any of these tricky silent data corruptions that they haven't picked up in tests will be less likely to occur if the core temperature is lowered. Next, they try and optimize the actual testing itself to be more efficient and take less time, which I'll explain momentarily. And finally, they employ a more fine-grained scheme for decommissioning processors. So the way this works is something like this. For starters, they optimize for efficiency by prioritizing test cases. During the pre-production tests, they simply run all of the tests with equal priority as they were doing before. However, during the regular tests, they prioritize tests which have found a fault. So tests which have already found a fault in other CPUs will be given more time, and tests which haven't found anything will be given much less time. This corresponds with their observation that most test cases don't find anything, and their guess that any test that all CPUs are likely to be vulnerable in the same way. Therefore, they assume that if a test case has already found something, it's more likely to find something in other CPUs of the same microarchitecture. And anything that hasn't found anything is unlikely to find any faults. And finally, they employ a more fine-grained decommissioning scheme for processors in which if they can identify a fault that's isolated to a single core, they only disable that core. And they don't remove the entire CPU until they detect more than 2 defective cores within the CPU. So at the end of the day, they've compared it to their baseline testing system and on a couple of CPUs with known faults, and found that during a single round of regular testing, Farron was able to detect a higher percentage, or at the very least the same amounts of the total percentage of known fault defects in that CPU when compared to the baseline. So one round of testing was able to find more faults, i.e. it's more likely to actually find any faults at all. It was able to do this using in far less time. In particular, the baseline system took over 10.5 hours to run a single regular testing round, whereas by prioritizing tests that have already found things, they were able to trim it down to just over an hour on average. Even when you count in the additional overhead at runtime from slowing down the CPU for thermal throttling, as they have a temperature control system to reduce the present likelihood of tricky STCs, Farron still has a substantially lower overhead than their baseline system in all of the CPUs that they've tested with. Okay, so now that's basically all the content in the paper. Let's look at some of its strengths and weaknesses. First strength, this is basically one of the few large-scale practical studies of silent data corruption in the wild, with the only exception being the other 2 papers by Facebook and Google. And importantly, it provides substantially more data than either of those 2 papers. It's got a lot more precise numbers as opposed to vague words like about, roughly, a few. And it also provides a number of completely new measurements and metrics that weren't provided by either of the other 2 existing papers. They also do, in fact, manage to propose an optimized testing strategy, which they demonstrate is able to detect more faults in a short amount of time and reduces the probability of silent data corruptions from undetected faults using a temperature control system. At the end, they also point out a number of opportunities where future work could expand on their findings. On the other hand, the paper still does omit a lot of data. There are still a great many points where they use vague quantifiers or simply skip out values that would have been interesting to see what they actually were, but they just don't mention at all. Presumably also still for business reasons, but it is unfortunate. They mentioned specifically that despite having a very large data set of millions of CPUs, they were actually only able to analyze 27 faulty CPUs. Apparently, most of the defective CPUs that are identified are immediately returned to the manufacturer, and they were only able to keep 27 of them for further analysis themselves. Some of their observations don't make much sense to me. For instance, they identify the vector unit and the FPU, the ALU, cache coherence, and transactional memory as being particularly vulnerable features of the CPU. I mean, it strikes to me that that's nearly all of the important features on the CPU already. It might have been more interesting if they had mentioned which features aren't particularly vulnerable to data corruptions. Also, their mitigation strategy is somewhat boring in that they aren't actually addressing the underlying problem. They don't actually attempt to solve the problem, nor do they attempt to detect when silent data corruptions have occurred in the wild. They simply try and reduce the number of tests that they're running to make the test phase go faster, and then lower the temperature so that maybe it won't happen as much. Presumably, this is simply a quick and dirty economical fix, which they didn't want to have to put too much effort into. But it is, it feels like there could have been more interesting approaches they could have taken. It's also problematic because they're training on their testing data set, in that by focusing only on test cases which have already found faults, it means, sure, they're increasing the likelihood that they'll pick up other faults of that type, but we don't know if maybe in the future, as the silicon degrades, maybe there might be a new kind of fault that can only be detected by one of the test cases that got deprioritized. So their system is biasing them towards their own observation that they've made, that only some test cases actually find faults. If a new fault test case started to find things in the future, it wouldn't be picked up. There's not very much interpretation or reasoning behind many of the observations that they make. For most of the time, they just give a number without really trying to explain or understand why this is occurring. And sometimes even when they do attempt to give an explanation for something, it doesn't end up making too much sense. For instance, in the case with the temperature control, they assume that the SDCs are correlated with temperatures, but they make no attempt to correlate the occurrence rate of SDCs with any other metric, such as frequency or temperature or voltage, or such as frequency or voltage, which might have been interesting to compare as well. And finally, for their testing scheme, they don't provide much evaluation data. The actual evaluation data is barely one paragraph. It seems like it would have been interesting to have evaluated their improved testing scheme across more than 6 CPUs, maybe across some TPUs that weren't actually known to be faulty. All right, so before we move into the discussion, are there any questions about what I've discussed so far? Mm-hmm.
What are the possible reasons for SDCs? Is it wear out? Is it well, why do they happen, and why do they happen undeterministic?
Yeah, I actually have a backup slide for this, but basically it is in fact due to wear out sometimes, but it can also just be general any kind of design defects, any kind of like manufacturing imprecision. But yes, oftentimes they only materialize at a later date once the CPU is past its has already been evaluated to be successful, presumably due to some kind of wear outs. But the exact mechanisms aren't entirely understood and often are probably different for each case.
The microphones too. Whoever has questions. Any questions?
So I'm not sure if this is already a discussion point, but do you know if this has been or can be exploited, like in terms of security attacks? Maybe you've heard of a paper or something?
I don't actually know if there's been too much in the way of exploiting it. The problem is that oftentimes it's so hard to reproduce in the first place that it would be very hard to use it for any kind of exploit. Like if you're trying to use this to break into someone's account on a server, you'd have to know that this particular CPU that you've just gained access to is actually vulnerable to this kind of corruption on this particular core under these circumstances. And I feel like it might be a potential attack vector, but it would require so much advanced knowledge that it would probably be easier to use some other attack vector.
So I think in the beginning you mentioned that silent data corruption does affect systems. Do you know if the paper specifically points out certain faults that happened in their system because of silent data corruptions?
Yeah, actually, one of the examples I mentioned at the beginning involved a case where the checksum was computed incorrectly, and it caused the system to keep sending the same request over and over again, causing the whole system to slow down dramatically.
Hello? Oh, perfect. Okay. Maybe I missed it, but you mentioned at one point that the paper left out some data or data that you were looking forward to see, but I didn't think you mentioned exactly what data you were looking for. So that would be my most interesting part, because you said there was some interesting stuff that you were looking to see.
For instance, there's a couple of graphs that they put in the there's a couple of graphs that are in the paper, but they don't actually have like a table for them. They just have some like scatter plots. It's hard to actually tell where the data points are. Although also when they mentioned, I think that they have evaluated the effective instruction usage stress on the frequency of STCs, but they don't actually provide any data on like how frequent an instruction needs to be used in order to trigger an STC. They just mentioned that it can cause them if it's used frequently enough. There's a lot of small things like that across the whole paper.
Sure. Thanks.
So I think the CPU vendors usually publish erratas about potential faults about the CPU. Are these included in the erratas, or because they happen indeterministically, they won't be included there?
Generally, that would be included because they're pretty much all like kind of one-off manufacturing defects. So it's not really a design flaw. It's more of just one faulty chip in particular. All right. Well, if there's nothing else, then I guess we can move on to the discussion. So my first, back up, wrong button. Okay, so my first question was, how could we attempt to mitigate silent data corruption in hardware or in software? If anyone has any kind of approach I'd like to suggest.
So a naive way would be to duplicate computation and then cross-check if all of the computation are correct.
Yeah, that's definitely an approach. That's actually something that is done in practice in certain cases. I think automotive systems, like there's a couple of self-driving cars that have duplicate CPUs, for instance. So that's definitely a viable approach, although it costs more. All right, if no one else has anything, keep pressing the wrong button. Yeah, so as you said, we can add some redundancy. We can just compute everything multiple times and make sure everything matches. Something that's done in particular, like in some military applications, is simply don't use the newest manufacturing process. If you have really big transistors, then sure, it's not necessarily as fast or power efficient. But if reliability is your key, then you're a lot less vulnerable to some kind of tiny manufacturing defect if your chip is so wide that the manufacturing defect doesn't have any measurable impact. All All right, so my next question would be, how could we try to improve test coverage for silent data corruptions? Like just at a high level, how could we try to make tests that pick up more faults, minimize the number of things that get missed? All right, there's more.
It was basically by using feedback from such manufacturers that have found STCs and curating test cases that can identify such faults.
Yeah, exactly. I think that would be kind of one of the key points, is just more communication between customers and the manufacturers. We could also have like better documentation on how the CPU is actually structured. Of course, this could be difficult for business reasons. Companies don't necessarily want to publish a full schematic of their CPU, but if the manufacturer isn't willing to write full exhaustive testing for every transistor on their CPU, then it would be nice to at least have a better idea of how the CPU is structured at a low level. And yeah, so more cooperation is also a good thing. We could have, for instance, shared test suites. At the moment, each kind of company with data centers seems to have their own SDC testing system. It would be cool if those could all be made public and shared with everyone so that everyone could benefit from improvements there. It could also be possible to have just the chip itself be more designed for self-testing. So just have some, maybe, I don't know, extra instructions, extra pins to enable some kind of a debug mode to help identify faults in itself. Okay. So what factors might cause STCs other than the core temperature? Do you want to say something?
I think you mentioned temperature and frequency before, if those could affect stuff, but maybe I don't know how realistic this is, since it's but maybe mechanical. There could be mechanical impact, for example, through like vibrations on the main board through, I don't know, maybe the cooling system.
That's actually, I hadn't actually considered that, but that's definitely we have frequency and temperature, I guess also, yeah, but that's definitely something that could be an issue, or maybe some kind of like thermal expansion, maybe. All right. One thing that also was mentioned in the paper briefly, without too much detail, was the rate at which an instruction is used. For instance, if a CPU has like multiple execution ports for a particular instruction, it might be that, and only one of those ports is actually defective, it might be that you might not ever actually see a data corruption unless you're using the instruction enough times per cycle that actually both execution ports are being used. How could we work on detecting or mitigating silent data corruptions in consumer software? Because in data centers, it's easy for the company to say, okay, we're going to reboot all the servers on this rack and we're going to run tests for 10 hours and then reboot back again. But on consumer devices, typically no one wants to have a laptop randomly run self-diagnostics for 10 hours at a time. What could be some other approaches we could take for running diagnostics on consumer devices?
Maybe because in a consumer device, not like a server one, which basically runs all the time, consumer only basically has challenging workload some parts of the day. And so instead of batch running all the 10 hours of diagnostics work, you could just run a couple of very small tests once in a while that don't affect the consumer's experience, but still occasionally might catch a defect.
Yeah, that's pretty much what I was thinking as well. If anyone else has any ideas, then they can mention them. Otherwise, I'll just move on. But yeah, so I also was thinking that maybe we could do some kind of like, in addition to that, like maybe during an update, you could just like kind of run a couple of minutes of tests. Just people expect the update will take a couple of minutes anyway, so maybe they won't care about an extra 3 or 4. But yeah, for longer testing runs, it would be better to do when the system is just idle. I was also thinking we could add some kind of like software redundancy. So for code that's actually critical, so like no customer cares if one of the pixels on their movie they're watching is the wrong color for one frame, but maybe they do care if they accidentally send the wrong number of francs to their friends or their, I don't know, in some transfer. So maybe code that's actually critical, we could emulate redundancy in software by manually running it on multiple cores and combining results. How could we work to detect or mitigate silent data corruption in peripheral devices? So since this is a hardware issue, there's no reason that GPUs or the little processor in the flash controller on your solid state drive might not also be vulnerable to silent data corruption. How could we work to test those? Okay. My main idea was more support from the manufacturer from this sort of thing. So first one being some kind of diagnostic mode. So like if you want to, I don't know, have some extra flag which you can set in order to reboot your solid state drive controller or your network card controller or whatever into some kind of alternate operating system which allows it to run self tests or maybe even just run arbitrary code. Obviously a potential security vulnerability, but maybe if it just allows manufacturer allowed tests, that could be an option. Additionally, like for instance, we could run tests on a GPU would be more useful to do if we could actually control, for instance, which of the GPU cores are actually running each test case. As like current GPU compute models, for instance, don't really allow you to specify, I want this to run on this particular core on the GPU out of 10,000. So that maybe if we had some kind of extra OpenCL function or whatever, that could be an approach. But again, potential security concerns may not be worth it. All right, that's all from me. If there's any questions, then. Well, I think that's it.
Thank you very much.
Yeah, let's have a 5-minute break to set up the next. Did they announce that? Large majority of people. Let's go.
Right, like, where am I supposed to put it?
I think
Here?
it's
Yeah.
the other way around.
I don't know.
Yes. It's really weird. Yes.
Okay.
You can just put it in your pockets. Don't worry about the time.
Wait. Does it work? Oh, this works.
Hello, hello. Can we start? Konstantinos, we are about to start. Sorry. Konstantina for plural. She's confused now. So we are going to start with the second presentation now. It's my honor to introduce Anna. I'm not going to try to say her last name. So she is currently the first semester of her master's program in computer science in ETH, specializing in data management systems, and she's interested in low-level system programming. So before she starts, I want to briefly say that you might get confused at some points in this talk. We are also confused. We are going to get to those confusions at the discussion points. So bear with us. Bear with Anna for some seconds. So feel free to start.
Okay, so hi everyone. Today I'll be presenting a paper called Harpocrates Breaking the Silence of CPU Faults through hardware in the loop program generation. And the paper was developed earlier this year at the University of Athens. So let's start from executive summary. So the problem here we are trying to solve is modern CPUs basically face increased risk of silent data corruptions due to defects aging or something like that. And basically traditional fault detection methods are just insufficient, therefore threatening system reliability. And the goal here would be to employ effective ways for the detection of potential CPU faults through the generation of efficient functional test programs. And the contribution of the paper is Harpocrates, which is an automated and hardware of our framework for generating CPU test programs to maximize fault detection across components and fault types. And here, basically, the framework consists of three main components. The first one being a generator that generates valid functional test programs, then a mutator that alters the current set of programs to create new variants, and finally, we have evaluator that assesses all generated programs against a predefined metric. And the results are the following. Harpocrates basically achieves nearly full fault detection in all tested function units and 10 times higher detection in the integer register file, outperforming other frameworks. It also generates test programs 30 times faster than current methods. And finally, it also delivers 10 times higher coverage for SSE FP units, twice higher coverage for both integer adder and integer multiplier, and 3 times greater coverage for the integer register file compared to the other leading frameworks. And now, as of overview, we are going to start with motivation, then we'll move on to background and take a look at the existing frameworks. Then we'll look at Harpocrates. We're going to move on to evaluation results, conclude, and then we are going to move on to strengths, weaknesses, and finish it off with some discussion. So now, as of motivation, basically, without a doubt, modern CPUs needs to handle complex workloads and massive data, and that basically increases risk of data corruption, system crashes, or just information loss. And hyperscaler basically report high levels of defective parts per million for CPU deployed in their fields. And as we can see, basically the numbers are way higher than the acceptable zone. So now moving on to background and existing frameworks. So this was already covered in the previous presentations. I'm just going to skip for it. And now we are going to take a look at the other important terminology, which is fault. And this is a physical defect in the CPU that results in the deviation from the expected operation. And there are 3 types of faults. The first one being transient faults, and those are temporary non-recurring faults. And those are just simply bit flips for a single cycle. Then we have intermittent faults that they oscillate between faulty and fault-free states. And finally, we have permanent faults that are basically persistent and unchanging faults that are stack at gate faults. And now moving on to the existing frameworks. So here we have first MeBench, which technically is not a framework, but it's just general purpose benchmark suite. Then the second framework is Silifus that was developed by Google, and it's fuzzing-based test generating framework using CPU simulators and disassemblers. And basically the main feature of this framework is that it's hardware agnostic, and therefore as a limitation, it basically generates many invalid or crashing sequences. And the final one that we're also gonna take a look at is OpenDCDX, and those are basically manually crafted tests focusing on specific CPU functionalities. And the main feature is that basically it can be tailored according to the needs by user, but also that comes as a limitation that it requires manual detailed input. And now, as of evaluation, so what's the setup, experimental setup? So first, we are gonna insert faults into a specific CPU component. Here, we are gonna target 6 different CPU hardware structures, which are integer register file, L1 data cache, integer adder, integer multiplier, SSE floating point adder, and SSE floating point multiplier. And then we are gonna generate functional test programs using a selected framework or just use the already provided. Then we are gonna simulate those tests in a faulty environment. And for that, we are gonna use Gen 5 microarchitecture simulator. And for fault injector, for transient faults, we are just gonna insert bit flips. And for permanent faults, we have gate level stacked faults. And finally, we're just gonna classify the outcomes for each test. And now, before we move on, we need to take a look at the important metrics that will be used in the evaluation. So the first one is hardware coverage, and basically this is represent how much of the CPU program is actively engaged during the execution of a test program. And basically and it depends on which type of CPU hardware structure we are examining. So for bit array structures, we are employing architecturally correct execution, ICE, and basically it calculates how many of the cycles for each bit are critical for the execution, comparing to the total number of cycles. And the second one, the second metric is input bit ratio, which is used for functional units. And basically, this the fraction of input bits exercised during the program execution to the total theoretical maximum input bits. And now, as of the second metric, so basically it's fault detection capability, and this is just the fraction of faults detected by the program compared to the total inserted faults. And for that, we're gonna employ statistical fault injection that it injects faults at the microarchitectural level and observes the outcome at the software level to estimate a program fault detection capability. And here we have 2 different outcomes. So the first one, possibility is mask, and this is when basically the program returns the correct answer. Like the expected answer, and the detected is when silent data corruption. So for example, when the fault propagates without disturbing the program, yet it returns the incorrect result, or just simply application system crash when basically fault visibly disrupts program execution. And now, before we're gonna move on, first let's quickly go through how to actually read this graph, because it might be confusing. So first, on the left, we have coverage metric that is measured by either IC or IBR, depending on what hardware structure we are targeting. Then on the right, we have detection, and this is basically the fraction of faults that has been successfully detected. And on x-axis, we have basically represents benchmarks tested against set of faults. And finally, what's worth noticing is that for coverage and detection, those scales might be different. So now, actually going to the baseline coverage and detection. So first, for integer register file, we can see that the detection capability for all XSI frameworks are pretty low, below 5%. And for L1 data cache, here we can see that detection capability is significantly higher than for the integer register file. And basically, there's one outlier, an OpenDCDX program that achieves 80% detection. But what's important to notice here is that ICE here serves as the upper bound for the detection capability. And here, like, the conclusion is that given the large gap between the coverage between the coverage, which here serves as the upper bound, and the measured detection that leaves us with a significant room for improvement. And now moving on to functional units. So the first one is integer adder. Here, detection capability is around 80% for all frameworks. And there are also single outliers for MeBench and OpenDCDAC that reach 99 and 98% of detection respectively. And for integer multiplier, here we have detection capability varies a lot between all three frameworks, with 53, 70, and 47 for all three frameworks respectively. And here again, what's important to notice is that IBR does not serve as the upper bound for the detection capability. And now finally, we have SSE floating points. So we can see that those units are not heavily utilized by many of the considered workloads, and only for MeBench and half of the OpenDCDAC benchmarks have non-zero detection. And OpenDCDAC performs best with maximum detection for SSE FP adder of 98.5, whereas for SSE FP multiplier it's only 58.2. And again, here the conclusion is that high coverage and low detection in those functional units indicate software masking, therefore emphasizing the pressing need for improved test development to efficiently identify permanent gate level faults. And now let's take a look at Harpocrates. So what are the challenges that Harpocrates is trying to solve and is facing? So first, basically modern CPU design and deployment, that we have multiple interacting hardware and software layers. Then we would also be able to target specific hardware structure for root cause and analysis. And then finally, we would like to minimize downtime. Therefore, we require fast, automated, and effective test programs. And Harpocrates basically framework combines simulation-based feedback and microarchitectural knowledge, and it evolves test programs to achieve superior fault detection and coverage. So now, taking a look at the high-level architecture. So as mentioned previously, Harpocrates consists of three components. First, we have generator that basically produces the initial set of test programs. Then we have evaluator that it ranks programs based on hardware coverage and fault detection. And then we have mutator that it alters programs to generate new variations. And now taking actually like a detailed look at the flow of Harpocrates. So again, first, Harpocrates basically utilizes music gen engine for both mutator and generator generation. And basically it generates the initial set of programs and it ensures the adherence to target ISA rules. And then we basically simulate and evaluate those programs using GM5 simulator. And basically we collect metrics such as hardware coverage and fault detection capability. And previously collected metrics are then used to give scores to each programs and then evaluate them. And then finally, we basically choose top K programs for further refinement. And then those programs, again, we utilize music gen engine to mutate those programs and generate new variants for the next evaluation cycle. And then again, we perform basically optimization loop and we repeat the cycle until convergence or just desired performance is achieved. And now to actually see what does it mean that CDFUS is hardware agnostic and Harpocrates is hardware aware. So let's take a closer look at the actual test case. So first, we can see that CDFUS, it basically represents the program as byte sequence, and it just mutates raw bytes with no internal notion of x86 encoding, and that basically results in 2 out of 3 produced sequences being invalid and eventually unusable. However, initially, Silifus basically adds them to test scores, but then later disregards them as non-usable. Whereas Harpocrates basically, as is ISA aware, does it basically generates instruction sequences accurately according to the ISA rules, and then it also relies on accurate hardware feedback from the execution of the program on Gem5 simulator to decide which of the mutated programs should be advanced to the next generation. And now let's take a closer look at the implementation. So basically, Harpocrates uses MuSecGen as the generate and mutator engine, and MuSecGen basically utilizes and heavily extends microprobe, which is an ISA-independent, modular, and extensible code generation framework. And it consists of 2 main modules. The first one being architecture modules that basically consists of configuration files that specify ISA details, and then we have code generation module that orchestrates a code generation process. And now microprobe does not initially support x86 ISA, therefore Harpocrates had to extend it to be able to support it, and the following steps had to be performed for that. So first, they had to identify x86-64 ISA reference files in a machine readable format. Then they had to develop a parser to be able to convert those files into configuration files, and then finally incorporate those files, configuration files, into the architecture module. So those files could be utilized to produce valid x86-64 assembly. And then this basically resulted in 2000 x86 instruction variants. So now moving on to evaluation and results. First, let's take a look at the generation speed. So basically, Silifus is the only framework that generates tests automatically, therefore it's the only viable option to compare it with. And here we can see that Silifus instruction generation rate is 1200 instructions per second, whereas for Harpocrates is 36,000 runnable instructions per second. Therefore, it's Harpocrates basically achieves 30 times faster instruction generation rate. And now taking a closer look at coverage and detection, again, we basically use the previously experimental setup. So for integer register file, Harpocrates attains more than 3 times the coverage compared to other frameworks. For L1 data cache, here we can see that Harpocrates achieves maximum coverage of 95%. And one conclusion is that basically injected transient faults and 2-bit array components are just much harder to detect for all frameworks compared to permanent faults and functional units. And now moving on to integer adder. So here, basically Harpocrates saturates at 10%, and therefore it achieves twice higher coverage than other frameworks. For multiplier, similarly, it saturates at 6%, and again, it achieves twice higher coverage compared to other frameworks. For SSE FP adder, it saturates at 7% coverage, and it achieves more than 10 times increased coverage. And similarly, for multiplier, it saturates at 5% coverage, and again, it achieves 10 times greater coverage. And basically, the conclusion from those results is that the increasing the coverage of the test programs we translates in increases in detection capability. And now taking a look at the detection. So here, basically, a register file detects nearly 10 times more faults compared to other frameworks. L1 data cache, so what's important to also notice is that the middle line, if it exists, it indicates the average detection capability. So here, average detection capability for L1 data cache, it's basically, it's roughly 20% for non-Harpocrates workloads, and whereas detection capability of Harpocrates basically approaches 90%. And now for integer other, and so here basically nearly all frameworks achieve nearly full detection. For integer multiplier here, the average detection for non-Harpocrates workloads are lower, like between 40 and 70%, whereas Harpocrates reaches here 100% detection, almost nearly 100% detection. And finally, we have SSE folding points, other multiplier. So for other, average detection is pretty low across non-Harpocrates frameworks, and Harpocrates basically achieves 99.8 detection, and it outperforms OpenDCDAC outlier that peaks at 98.5. And here for multiplier, the average detection is even lower. And basically the highest detection is for OpenDCDAC program at 58.2. And finally, Harpocrates program reaches 99.7%. And basically, we can conclude that Harpocrates is the only framework that reaches a nearly full fault detection in all tested functional units. And now, to conclude, basically the paper introduced a novel methodology for automatic generation of functional test programs, and it complements existing frameworks with a hardware-in-the-loop approach, leading to increased detection capability. And then as a result, basically Harpocrates improves CPU fault detection by generating test programs 30 times faster than current methods, and it also achieves nearly full detection across all tested functional units and 10 times higher detection in integer register file. And now moving on to strengths and weaknesses. So the first one would be that Harpocrates basically introduced unique approach, hardware-in-the-loop methodology to generate those effective test programs for CPU fault detection. Then it's also hardware, therefore it basically doesn't lead to many crashing sequences comparing to, for example, Silifus, and it also helps to and also leverage detailed feedback, microarchitectural feedback for more accurate and targeted fault detection. It's also efficient comparing to, for example, Silifus. It generates test programs faster. It also is wide applicable because demonstrates is adaptable for many fault types, and also it's thoroughly tested in the paper, whereas such as against multiple hardware structures and fault types. However, that also I didn't find it as for us I would like, because, for example, we didn't get validation against a full CPU system. Another weakness would be that basically all the faults were all the results rely basically on software-based fault injection and evaluation and simulation, and we didn't really get any testing on actual CPU prototypes. Moreover, basically the effectiveness of Harpocrates, it depends on the underlying simulator, GEM5, and fault injector, GFIN. And also the primary focus remains on transient and permanent faults and disregards intermittent faults. Another weaknesses would be that basically we didn't really, in the paper, I liked information about what type of faults were injected and how many of those faults were injected. Then also I found a lot of errors and overstatements. There were a lot of inaccuracies, for example, graph showing 0.7% while the text stayed 7%. Then that the paper claims suppressing need for functional framework due to a combination of high coverage and low detection. But on the graphs, it was not really well supported. And also, for one of the baselines, they said that only half of the OpenDCDunk programs have non-zero detection, whereas Silifus detection for SSE, FP, other and multiplayer was like around 40%. And also, personally, I really found it hard to read. The flow of the paper was just simply not logical, and also missed critical details or just some information. And finally, basically there was no public repository provided, any code. So yeah, before we get to the discussion, are there any questions?
So I still have a general question. Can you maybe explain why the fuzzing happens on on such a low level, and why they couldn't use, for example, a standard fuzzing tool that works like, let's say, on a programming language level?
I'm sorry, could you repeat?
Yeah, so my question is, there's a bunch of tools that can generate random programs, right? So why don't you use that, generate a random C program, compile it, test it, and then modify the AST or something? Like there's fuzzers out there that exist.
I think that's a good question, and I don't have an answer for that. I think I didn't look into that, but yeah, that's a good point.
I think if you randomly modify code at the C++ level, for example, the compiler might optimize away things that you're inserting anyway. Like if they're not used downstream, then it's just gonna optimize it away. It's easier to impact the hardware by directly operating at the instruction level. I mean, that's what I think about it.
Okay, so now moving on to discussion. So the first one would be how this methodology, like Harpocrates, can be actually integrated to the production environments. Okay, so I think that basically here we would need to consider whether we want to periodic maintenance or just on-demand testing, whether we suspect faults in CPUs and then we want to run it, or like as mentioned in the previous presentation, for example, before every update, we can check those CPUs, and then but also we need to consider substantial resource overheads due to running all those tests. And now, as of the second question would be, given that, like, do you think that Harpocrates would be also effective addressing faults across the entire CPU system as a whole? Because here we just saw in the paper that they were like only focusing on specific hardware structures. Yes.
My understanding is that you use specific instructions to target or test, essentially. So given that an instruction can touch a particular part of the system, it will be able to detect or cover those faults. But if certain components require a lot of instructions to touch, then it becomes complicated.
But also, like, I think that here's that to mutate the test, like basically to assess what tests are going to the next step. Basically, we are using the specific like prefi metrics, and for that we are utilizing IC or IBR. So I think that the problem here is that, like, basically the simplest solution, how I thought it would be, just combine all test sets that were like targeting each specific hardware structure, and that would be basically the simplest. But of course, not the best idea. And then if we want to try to, like, for example, target the broader system level, we would need to adapt the fitness function to basically decide what programs would need to go to the next step. And now the final question would be, would this approach, harbor and loop, also work for detecting faults in our processing units such as GPUs or TPUs?
I don't see why it wouldn't. I mean, assuming that you have a schematic or design of the GPU or TPU that you're testing, it would be difficult to get one of those, but that's a separate problem. But yeah, I think it would probably be a bit more difficult to then actually act on those results simply because you probably still have to do some communication with the CPU, but I don't see why it wouldn't work.
Yeah, like also think that like the general idea would work for other processing units, but only I think that just simulation might require substantial resources, and that might be just more difficult to achieve high coverage and fault detection. And yeah, that would be all. So thank you very much.
Please remember to give the feedbacks to the presenters since it's close to the end of this semester. I think that's all. And please also check the previous feedbacks. You can also give feedbacks to the previous presenters. You can do that until the end of this month. Yeah, that's all. Have a nice day. Bye.
Ja, das habe ich.